Hello, in this video we will consider law of conservation of charge. There are several laws of conservation in physics. Now we take up this law of conservation of charge. We will see what it is and the corresponding explanation. The statement of law of conservation of charge is this: total charge of an isolated system is always conserved, that is, remains constant. So conserved in this context indicates remains constant, or you can even state it in other words: charge cannot be created, not destroyed. It can be transferred from one place to the other. This statement was first put forward by Benjamin Franklin. Is it clear? So total charge in an isolated system remains same, even though the internal distribution of charges may change. Some charge may go from one place to the other, but the total charge will remain same. If the total charge initially is 0, finally also it will be 0. Initially means at some instant of time, finally means after some interval. Okay. Now you take this example. Say you have a glass rod and a silk cloth. Initially we assume them to be neutral. This has not been electrified. This has not also been electrified. This carries no net charge. This carries no net charge. Now this is an isolated system. Okay, glass rod and silk cloth. If you want, you can imagine somebody else inside the system, so that he will rub the glass rod with silk cloth. For this activity, you can imagine someone does this activity, is also part of the isolated system, but we assume that the person is not getting any charge from these two, or is not also giving his charges to these two. He is simply playing the role of rubbing the glass rod with the silk cloth. If the glass rod is rubbed with the silk cloth, the glass rod becomes positively charged and the silk cloth becomes negatively charged. How much positive it will be, how much negative it will be, depends on the amount of electrons that is getting transferred between the two. When a glass rod is rubbed with the silk cloth, the electrons can go from the glass rod to silk cloth. Thereby the glass rod becomes positive. Because it loses electrons, it becomes positive. Silk cloth, on the other hand, gains electrons and becomes negative. But the number of electrons this glass rod has lost is same as the number of electrons that the silk cloth has gained. We can say that the charge on the glass rod being positive is same as the charge on the silk cloth. Of course, numerically same, but with a negative nature. Okay, this glass rod becomes positively charged, silk cloth becomes negatively charged by the same amount, because the number of electrons glass rod has lost is same as the number of electrons the silk cloth has gained. Who will do the rubbing process? Say there is another person inside the system. He is only doing the passive role of rubbing the glass rod with the silk cloth. He is not transferring his charges to this glass rod and silk cloth. Neither he is taking up charges from the glass rod and silk cloth. He is only doing the rubbing phenomenon. Okay, so we will assume that, because we need someone else to do the rubbing process. Okay, someone else to do the phenomenon of rubbing, to execute the phenomenon of rubbing. Okay, now what will happen here? Glass rod has lost electrons. Don't think that only one electron is lost. It's only a symbolic way to say that the electrons have got transferred from the glass rod to silk cloth. Thereby the glass rod is becoming positively charged, the silk cloth has become negatively charged. Suppose the glass rod has become positively charged by an amount, say plus Q. Then the silk cloth would have become negatively charged. Say it will be negatively charged, say minus Q. Here what is the total charge? 0. Before the rubbing process, rubbing phenomenon. Now what is the total charge? 0, plus Q and minus Q. So total charge is 0, either before the rubbing process or after the rubbing process. Okay, it is in accordance with law of conservation of charge. Right. Now another example: ebonite rod, woolen cloth. Ebonite rod is rubbed with the woolen cloth. ebonite rod would become negatively charged, woolen cloth will become positively charged. That means now the electrons have tendency to go from woolen cloth to ebonite rod. That means the electrons go from woolen cloth to ebonite rod. How many electrons the woolen cloth loses, so many electrons the ebonite rod gains. Here also the charge will be equal in magnitude. Ebonite rod say minus q, woolen cloth it will be plus q. Total charge will be 0 even after the rubbing phenomenon. Okay, the third person is there just to do the activity of rubbing the ebonite rod with woolen cloth. We assume that he is not delivering any charges to the ebonite rod and woolen cloth. He is not also picking up any charges from the ebonite rod and woolen cloth. So this is the scenario. What will happen because of the rubbing phenomenon? Now the electrons have gone from woolen cloth to ebonite rod, negatively charged, positively charged. Minus q and plus q you add. Total becomes 0. Here also 0. Therefore, this is also in accordance with law of conservation of charge. Okay. So here why this glass rod becomes positive, whereas in this case ebonite becomes negative, or why in this case glass rod loses electrons, and in this case why woolen cloth loses electrons. It all depends on the work function of the materials that are there in the system. So higher the work function of a material means you need more energy to transfer electrons. Lower the work function means less energy is enough. So depending on the work function values, it so happens here the glass rod loses electrons, here the woolen cloth loses electrons. But after all the total charge is same, 0 before the rubbing process, also after the rubbing process. We have lot of examples here. This is true. Which is true? Law of conservation of charge. Even at the large scale level, large scale charge bodies like we discussed already, glass rod and silk cloth, etc. Also at the microscopic level, see, for atoms, nuclei and even elementary particles alike, this law is true. We can consider important examples. The first one is radioactivity. This one is what is known as alpha decay. 2He4 is alpha particle. This is helium nucleus. 92 uranium 238. That means 90. This is uranium nucleus. Radioactivity is a nuclear phenomenon. So 92 protons. Thorium has 90 protons. Helium has 2 protons. Plus Q. Q is the energy. That will be in the form of kinetic energy of these two. Now this is in accordance with law of conservation of charge. How? Charge before the decay. This is what is known as alpha decay. Charge before decay, 92. In terms of the charge on the electrons, considered numerically, 92 times the charge on the electron. Of course, considering it to be positive. Here, 90 plus 2. The lower numbers indicate charge. Of course, all the charges are positive. So 90 plus 2, 92. Before the decay, 92 in terms of the charge on the electrons, considered numerically. After decay also 92 times E. Have you understood? This is strictly in accordance with law of conservation of charge. Now also we can have a phenomenon called annihilation. That means if you have an electron and a positron, E minus electron, E plus positron, when they come together, understand that they destroy each other, they vanish, and two gamma ray photons are produced. 2 gammas are produced, at least 2. Okay, so electron and positron, this phenomenon is known as annihilation. That means they destroy each other and gammas are produced. This is also in accordance with law of conservation of charge. But before that, you should know what is this positron. So positron is what is called as antiparticle of electron. Charge on the positron is same as charge on the electron, but positive. Right, and mass is same both for electron and positron. So it is not enough that only charge is equal, but also the masses should be equal. Okay, see here, a positron is an antiparticle of electron. It is also called as positive electrons. Sometimes you use this wordings, positive electron. Charge on the positron is same as that of the electron numerically, but positive. Also the mass of the positron is same as that of an electron, right? That they destroy each other and gammas are produced. Total charge 0 before the annihilation. Also after the annihilation, total charge is 0. The next phenomenon, pair production. See here a gamma, which is energy. Energy is used up to produce these two particles, electron and positron. Charge before the pair production 0, charge after the pair production is also 0, because charge on the positron positive, charge on the electron negative, and they are value wise equal. Therefore, law of conservation of charge. No, great. Next one, very important notification. Very important note. Very important note. It is not possible to create or destroy net charge carried by an isolated system, although the charge carrying particles may be created or destroyed in a process. So charges cannot be created, charges cannot be destroyed, but charge carrying particles at times may be created or destroyed in some processes. Sometimes nature creates charged particles. A neutron turns into a proton and an electron in what is known as beta minus decay. The proton and electron thus created have equal and opposite charges. We know that charge on the electron is negative and equal to the charge on the proton. Of course, protons charge positive, electrons charge negative, but the magnitude of the charges are same, right? Neutron turns into a proton and an electron. So neutron charge 0. When you add the charge on the proton and electron, that is also 0, right? And the total charge is 0 before and after the creation. You see this. Neutron's charge 0. Proton's charge, if you consider plus 1 unit, electron charge minus 1 unit, total 0. This is anti-neutrino. Nu bar, no? Anti-neutrino does not have any charge. This is also strictly in accordance with law of conservation of charge. Have you understood this? Thank you. Please like and subscribe. Thank you once again.